lectures, one on incremental view maintenance and the second on sampling. And the first one will be given by Dan Olteanu on incremental view maintenance.
Thank you. Good morning, everyone. So we heard over the past days about lots of algorithmic problems. Some of them basically solved using dynamic algorithms. Incremental maintenance, view maintenance, is actually a historical old term for that type of fully dynamic algorithm, but done on queries in databases. So first, I would like to acknowledge my team, Ahmed, Hauge, Johan, and Milos. And also, I'm grateful for collaboration on this topic with my colleagues at Relation AI, particular Hung, Nico, Henrik, and El Saidi. So what is the setting? So as I mentioned, incremental view maintenance may be a misnomer because we don't mean only to increment, to add to the database. There can be also a decremental aspect of it. And an alternative common naming that is in the literature is fully dynamic, so that we support both inserts and updates. This has been a well-established and is a long-standing research problem, actually, in databases. So our setting is this. We look at both inserts and deletes. We look at complexities for doing single tuple updates to relational databases. And our interest is in queries, so maintaining the answers to queries under such updates. Now, towards the end, if I have the time, I will also show you something about maintaining, let's say, machine learning models, where, inspired by actually many talks talking about semi-rings and so on. I will show you a ring, if I get to that point, right? A ring for maintaining covariance matrices over joints in databases. And the kind of queries I'm going to consider are non-recursive. So this looks like a very limited scope. However, there isn't much known, nevertheless, besides a few classical approaches called delta queries, this umbrella, and I will exemplify this. There isn't much else known in terms of complexity, in particular optimality for these queries, and also how to whether there are trade-offs involved in, for instance, doing fast updates, but then the answer time may be actually slower, or having very slow updates, but then the answer time is fast. Yeah, and whether we can have a trade-off between these two aspects. The objective is this overview of recent and still to this day very preliminary results, on worst-case optimal incremental view maintenance, the trade-offs I mentioned, and if I get to it, IVM for complex analytics. So what is the incremental view maintenance problem? You see it here. We are given a query and a database. The query is considered small and fixed. The database is typically very large. And we are allowed to have a pre-processing step to create an auxiliary data structure. And that time it takes to do this pre-processing, we call it pre-processing time in this presentation. And out of this data structure afterwards, we are allowed to support access requests from users. And these are in the form of enumerate the tuples in the answer of a query. And to capture this enumeration time, we use the notion of enumeration delay, which is the maximum of 3 times. Is the time from the beginning to enumerating the first record in the database in some order, then to enumerate between one record and the next, and until the very end to enumerate from the last tuple to the end of the enumeration, right? So these are 3 times, and that would be for us the delay with which we do the enumeration. Why are we interested in delay? There are several reasons. One reason is that this provides a more fine-grained analysis of what's actually going on for that particular query, as opposed to just, say, looking particularly at the size. Because the size may be very, very large, yet the query may be very easy. So just looking at the size is not necessarily the right measure of complexity for some of the queries. Now, what I presented so far could sit very well in the static, I would say, query evaluation setting. For the dynamic one, we get an additional aspect, namely that here from the very bottom, we get updates, which may be to both database, but then we may have also to carry them to the auxiliary data structure. And the time to maintain this database and the data structure, we actually label as update time, right? So we have then the preprocessing time, the enumeration delay, and the update time. And we are interested in the trade-off between these three components of the complexity. Good. So the agenda is this. First of all, being aware of the fact that perhaps some of you are not database, experts, I will actually exemplify typical incremental view maintenance techniques by an example. And for that, I will use the triangle count query that will allow me to show you both existing upper bounds, new upper bounds, and also a lower bound. Then we look at, let's say, the kind of best we can hope for. Namely, can we get queries that have constant update time and constant enumeration delay? And this turns out to be the class of so-called Q hierarchical queries. And then we look at generalization from Q hierarchical queries. So what if we drop a property of the queries, this Q in front? Can we then, for instance, still attain some form of optimality is the question. And we will see that in detail. And at the very end, if time allows, I will actually show you how we can maintain models. In particular, I look at covariance matrix and Cholu trees, which are built on pairwise mutual information. In particular, motivated by talks before this talk, where we heard about such terms. So let me show you IVM techniques by example. So for that, first, let me establish the data model. Yes.
So how is this framework connect to the dynamic algorithm framework that we saw yesterday? So can you can you view these queries as kind of a special problem of the things we were looking at yesterday? Or?
So typically what I observed is that in the algorithms community, people focus on a specific problem that can sometimes be phrased as a specific query in databases. However, in databases, we try to reason about classes of queries, right? So for instance, triangle count would be one problem, right, in the algorithm. So that's my very biased understanding. But for us, it's one query in a larger class of queries, right? Another aspect which you will see is that whereas my understanding from previous talks was that there are completely different algorithms and different techniques and everything to deal with sparse and dense settings, sometimes we have to account for both such settings when computing the same query over the database, because the database may have parts which are both dense and sparse, right? So we have to put them under the hood somehow together, okay?
So do results transfer in?
I think yes. I think they transfer, and I will also mention very briefly that, for instance, the triangle count thing we did was later on extended by people in the algorithms community, right? To, for instance, do batch processing in parallel and all these other things. So there is actually, I would say, communication both ways. In the other way, for instance, lower bounds, we borrow from the algorithms community. Right? Like, for instance, this online matrix vector multiplication conjecture we've seen yesterday, this is exactly what I'm going to use more or less to show lower bounds for our queries. Yes?
Yeah, so along that line, yesterday we were told that we basically can't do anything better than brute force. So how can you do better? So do you know more information about data, or so what's the difference in the settings?
You mean for a specific query or in general?
So we saw there were many dynamic algorithms, and then at least result is that assuming some hypothesis, we can do better than brute force.
So it is true, however, that if we we have an additional parameter here, the structure of the query, and sometimes the structure of the query allows us to lower the complexity of the problem. So in many of these cases, maintaining the query result doesn't necessarily mean you want to maintain a listing representation of the answer of the query. You may maintain instead a more compact representation, which comes with the asymptotically lower complexity. Right. So this is, for instance, one aspect that is considered. Another one, which I will touch in the lecture, is that you can also use functional dependencies or other types of constraints that hold in the data. So you see, we can use on one hand some properties of the data, but also we may use properties of the query. And that makes it a bit richer, I would say, right? At least from a database perspective. So okay, so let me go back to the model, right? If there are no further questions. So we consider relations like this, right, with sets of tuples, but we actually extend them a little bit. So we see them, what is sometimes in AI is called factors, right? We see them as functions that map tuples to elements from a ring, okay? So here, for instance, I use the Z ring, and I use these numbers 2, 3, and so on to represent the multiplicities of the tuples. And this is actually very convenient for several reasons. One of the reasons is that it allows me to treat uniformly both inserts and deletes, because inserts will then be seen as tuples with positive multiplicities, deletes as tuples with negative multiplicities. But later on, I will replace this ring with a more complicated ring, where instead of this number, I will have actually complex objects that represent, for instance, partial covariance matrices, which can then be added, subtracted, and we then can maintain entire covariance matrices. So, but you can think of it, you can add here whatever, as long as it's a ring. If you cannot make it a ring, then it can be a semi-ring, in which case you can, just do inserts, right? Or you may have a very limited way of doing deletes. Yes?
What's the second operator in the ring?
Well, we have two operators, like in a semi-ring, right? We have the addition and multiplication, right? But the difference to the semi-ring is that we have the additive inverse. So you can have elements A and minus A so that their sum makes 0, which is the neutral element.
But what do you do? Does the multiplication play a role?
In this ring?
Yes.
Yes, it plays a role in the same way it plays, in K relations, in the sense that you have to, trace somehow the computation over these multiplications, over these multiplicities to the end result. So I will show you an example now. So assume that these are actually my tables, A, B, B, C, C, A. So this represents actually the column names, right, in databases, right? And then having a B here and there means that basically I have a natural join, an implicit natural join on the table R and S on this column B. Please apologize, Ahmed. He's extremely happy, His daughter was born yesterday, okay? And he's very, very happy about that. And of course, we talked about that, but I think he forgot that I'm giving a talk now. Which is completely excusable. And then, between S and T, we have C, right? The column C. And this means we also have a join there. And we also have a join between R and T on A. Okay? So if we do the join, R times S times T, what does it mean? It means that we look at tuples that match up, right? So we have the same B1 here and there, the same C1 here and there, and A1 from here and there, right? So we create a tuple A1, B1, C1, and what we do with the multiplicities, we just multiply them. So that's the effect of the multiplication we have here. And now we get the value of 4, but there are several other possible derivations, several other possible tuples in the answer, and in particular, we can get the other two here, right? And then if you want, for instance, to count the number of answers, which means you want to aggregate away or to, use variable elimination to get rid of A, B, and C, then you will get an answer which just maps the empty tuple to the sum of these multiplicities, which is 19 here. Yeah. So this is like in databases. Now, classical ones. Now imagine I have this update, and usually updates, I represent them with a delta in front. Yeah. And this says that I have a new tuple A2B1, which is mapped to -2. Yeah. So now I look up in the database for relation R, because it's a delta applied to R, and I see that indeed I have A2B1, and I have a value of 3. So what is the effect? The effect is that I have to erase this and now insert one which has A2B1, but now the multiplicity is only 1, because I had to take 3 plus -2. And that actually has an effect on the result, and namely, combining it with these blue guys here, ending up with this tuple here. That tuple has to be updated, and as you can see, we can delete this one and now add instead a new multiplicity 3, which then has the effect of actually getting an overall count of 13, not anymore 19. Now, this example already shows something quite nice, namely that as effect of one update to the database, you may not have to recompute everything in the database. You just have to compute just a few bits. Yeah. So the name of the game is, okay, can you propagate these updates in the simplest possible way, the most effective possible way, right? So we don't want to recompute from scratch. And this is why the incremental view maintenance problem gained so much interest, in particular because databases are large, it costs a lot of time to recompute everything from scratch. So could we, in fact, just recompute the little changes and apply them then to the result? Yeah. So that is the thing. And this is why also incremental view maintenance, this problem has a lower complexity overall, in general, I would say, well, for specific queries than actually just recomputing from scratch. So we are after this particular game. Yes.
After update, can the counts be negative? The update say -2, could you do -4 here?
So the question is, what happens if, I did already a -2, but now I want to do a -4 or a -2 again, right? So I will get something negative in here. So there are several interesting aspects to this. I would say that, at least in our formalists, we allow that. Yeah. So you have a temporary state of the database where multiplicities may be negative. What is the benefit? The benefit is that you can allow basically for updates to come out of order. And if you have a batch of them, you allow all of them to be, executed, and only at the end of the execution, you look and basically the interpretation is that whatever has a strictly positive, multiplicity is considered in the database. Whatever doesn't have is not in the database, right? But that allows me, for instance, to basically swap between an insert and a delete, and I can do delete first. This is nice for parallelization purposes, for various types of optimizations. It's also possible in the if you have this distributed setting, right? And then you cannot even want to enforce a particular order of the execution because it precludes the whole parallelization you can achieve. Yes.
Can you do an update on a tuple which is currently not in the database?
Yes, definitely. And this is also a very important aspect. For instance, if you be in a matrix case, you have n by n, you can only update something which is in there, right? Relations are more general, so you can insert something that doesn't correspond to particular coordinates, I would say, in a tensor or a matrix, right? So I could easily insert A3B1, which will just be added here, and then I will check with the other tables whether I have a join, and I may add something to the result. Right. So it's a fairly general thing. Yes.
So, and if you join two negative tuples, you get a positive one.
No. Okay.
No, but how do you resolve this actually? It's a valid question.
Okay, how you do this? Well, one aspect of how to do this is that when you actually have to do the multiplication, you have to actually account for that, right? So if you multiply things which are negative, you get something negative in the result. I think that this is because basically it means that they are out of there. They are not.
But then that doesn't correspond to the try and count query that you wrote. I mean, this tells you whatever multiplicities you have, you got to multiply.
Well, let me take this offline, right? So I can have a bit of time to think about that. Yeah. Okay. So, but it is true that basically, if you have several negative ones, the effect in the answer shouldn't be you actually add a positive thing, right? Because this is true. Yeah. So you have to do it. Thank you very much, Florence. So let us look at the triangle count query. So we have this. So this is the way we'll actually represent the query. So we take these factors as being these functions that map tuples AB, right, over the values AB to some element of a ring, S the same, T the same, and then we take a sum over ABC. Which means that basically by this I mean to say that I take A to iterate over all the values in the active domain, which is the possible values I have in this of A values I have in R and T. Then B will be the same from the active domain of B, and C the same. And then for each tuple ABC, I check whether R, S, and T are actually satisfied, and then I take their elements in the ring, I multiply them, and that will contribute to the overall sum. So the problem is, can we maintain Q under single tuple updates to RS and T? Okay. So there is a lot of literature on the triangles. So it served actually as a milestone in many fields. For instance, for worst case optimal join algorithms, so that was one of the workhorse, showing that actually we can get lower complexity than in the case of just using standard query evaluation techniques that join two relations at a time. Then in parallel query evaluation, so that was basically, there is an article by Uri Zurich, but there is also by Hung and colleagues. Then on parallel query evaluation, Dan Suchu and Paris, they actually use the triangle join query to actually show some interesting complexities, in particular lower bounds. Then we have also the randomized approximation setting, and there are many other settings in streams or static. For answering queries under updates, there is quite some work done by Nicole Schweikart. And there is a lot of system developments to which we also contributed. And we also have lower bounds, in particular by Virginia here. And these are things we are going to use. And also basically the OMV problem introduced in stock by Monika Hensinger. So the question remains, is there a fully dynamic algorithm that can maintain the exact triangle count in worst case optimal time? So there are several possibilities. The naive one is to recompute from scratch. So imagine we have the relations RS and T, and there is a sum, and we get a delta to R. We just incorporate it in R, and then we are left with the same query again, which we recompute. So if n is the database size, then the update time could be done in this n to 1.5 using a worst case optimal join algorithm, but could be slightly better using Strassen-like matrix multiplication. We already seen on slides yesterday, like n to 1.41, if I'm not mistaken. And then the space remains linear because you just store the input relations. Now, there is something which is actually the approach implemented in virtually all commercial database management systems, which is basically called delta queries. So here, you compute the delta. And what is the idea? The idea is that if you get this delta R to R, right, instead of just appending it to R and then recomputing from scratch, we just compute the join of delta R with S and T. Yeah. So because the delta R in our case is a single tuple update, has specific alpha and beta values, then it means that we only look at the part of S that has beta, right, for the first column, and has alpha for the second column in T. And then so we only need to basically sum up over C. So this arguably it is a simpler query as the original query, and in fact we just need to take the C squared with B and the C squared with alpha, and then intersect them, right? And that intersection may actually take a linear time in n, because in general, beta and alpha may be paired with n possible value C. So after we do this, of course, we just sum Q with delta Q and get the new Q, and the update time will be linear to intersect the C values, and then the space remains linear. And I wanted to also mention that this is called the first order incremental sometimes, because it is actually expressed at the level of the query, right? The original query. So you express the computation of the change just using another query, so first order query. Then this was introduced actually, this idea of first order to contrast it to the so-called higher order incremental view maintenance, which was proposed by Christoph Koch in his DB toaster system, where the idea is that you can take a delta of a query, but that query may have very many joins, and you can actually materialize some of these joins. Yeah. You create then views, and then you can recursively maintain those views. So you get a recursive maintenance scheme that maintains the first query by using some materialized views, and then maintaining also these materialized views again with their deltas. And this is why it's called higher order. So in this case, I want to show you for this query that what I can do, for instance, I can join S and T. I can get a materialized view that sums over C, and then I only keep B and A. Yeah. And after that, I have a simpler query where for which if I have a delta alpha beta, I can do then just simply a lookup in the view, and that will be cheap. And then for this reason, I can actually compute this particular update in constant time, assuming that the view is already materialized. But of course, the caveat here is that we also have to maintain the view. So the complexity is still there, right? We still have some linear complexity in maintaining the view. And this is how it happens. So if we have, let's say, the view where we join S and T on C, and then we aggregate away C, then if we do a delta to S, right, then this beta gamma, which is basically the tuple in S, in delta S, will then look up in here. And for a gamma, we may have very many A's, may have linearly many A's. So the complexity for that remains actually linear to do this. Yeah. In DB-Toaster, in fact, Christoph basically maintained all the pairwise joins, right? Maintains the actual view for ST, for RS, and for RT to get updates. Good. So, but the space here, however, is the problem, because we have to pay for the price of materializing this view, right? With the hope of speeding up at least inserts to R. So now, knowing that, for instance, R may be the only updatable relation, this really pays off, because you materialize the view once, you don't need to maintain it, and then the lookups into the view will be cheap from all the updates you do to R. Yes?
I don't quite understand, in the DB-Toaster approach, if you have to materialize all these extra views, how do you gain anything? I mean,
So, okay, for this particular query, you will not gain anything, you're right. Yeah, but if you only materialize ST, you will gain.
Sure.
Yeah.
And how are you going beyond first order maintenance here? What is this?
So the idea is that you get this view materialized, yes, right? So the query becomes simpler, and then you have to materialize the view, as well. So you have to.
But the views had the first order definition over.
Yeah. No, it's also materialized. So it's also stored on disk.
Oh, I see. So it is materialization.
Yeah, exactly. Yeah, which may actually speed up sometimes. Yeah. Okay, so these are actually some techniques which are quite common, I would say, in IVM, right, for databases. Now, let me actually show a different tool in the toolbox, which we may use, which is basically how to show lower bounds for maintaining the triangle count. So for that, I will look actually at a simpler version of the query, which is the Boolean triangle detection problem. So effectively, I have the query, but now I'm interested only in whether there is at least one answer, right? And not counting the answers. And basically, for this particular triangle detection query problem, we can come up with the following statement that for any strictly positive gamma, there is no algorithm that incrementally maintains the query with this update time, right? And this enumeration delay. So what does it mean? It means that here we have n, the size of the database at the time we do the update, and then it's to the power of 1/2 minus this gamma. Yeah. In particular, the question remains whether we can have an algorithm that can achieve it in O of n to 1/2. Right, because going below is not possible, and then the enumeration delay is just in this case it says that it can be linear.
What does the enumeration delay? It just means getting the answer.
It means answer time. Yeah, so you want to get the answer.
And do these two lower bounds apply simultaneously or individually?
No, they apply together. It's not possible to get this and that. Yeah, and we will see later that this actually leads to some weak Pareto optimality for some of our results, in the sense that we can have an algorithm that matches both, but it is still possible that you keep one as presented here, and the other one can be decreased, right? So that still remains, but we'll get there.
So now, is there a typo here? Because I was expecting one to grow, the other to shrink as gamma grows. But here, if I choose gamma to be very large, it means I cannot have no, if I choose gamma to be very small, it means I can't have, and yeah, so are you sure it's minus minus here?
Well, I surely hope so, because I'm going to show the derivations of the proof.
Okay.
Yeah, but yes, yeah.
But then this is a lower bound. So basically,
lower
you can't drop, in both cases, you can't drop under half and under 1.
Yeah, yes.
So, but for that, I'm going to use a rather more involved conjecture.
Sorry, I'm still confused. So if it's a lower bound, then I want to choose gamma as large as possible. So as small as possible. I want to choose gamma to be 0. Now, isn't that the best lower bound I can get if I choose gamma to be 0?
Well, I mean, gamma has to be strictly greater than 0. And what it says is that you cannot go below both of them at the same time.
Right, but if I choose gamma very, very small, that's kind of the best, and it means n to the 1/2 and n, and that is the strongest lower bound.
Yeah, the conjecture says you cannot do this.
Yeah. So this says you cannot do this.
I mean, it's very similar to these statements that say for every epsilon, you cannot get into the 3 minus epsilon times.
Yes.
It's analogous.
Okay, so let's see this. So first of all, let me define this OUMV problem. So input would be an n by n Boolean matrix, M, and we are given n pairs of vectors, u1, v1, un, vn, right? And these vectors also have size n. And what we want to do is the following. We want that after seeing every pair, we want to output this computation, which is the UR transpose M times V, the index R, right? And that would be a scalar. Right. So now the idea here to make it dynamic, as also Virginia explained yesterday, is essentially to force you to output after seeing every pair of vectors, right? So it doesn't allow you to, see more columns at the time, more vectors at the time, and then you may do some Strassen-like combinatorial arguments, right? So, and this is what we are going to do. So effectively, we want to be able to show that solving this problem, we can solve this problem using our query. Okay, so the OMV conjecture stated by Monica Hensinger is the following, and others, yeah. For any gamma greater than 0, there is no algorithm that solves OUMV in time of n to the 3 minus gamma. So effectively, you cannot get it in subcubic time. Yeah, the overall, right? So yesterday we've seen it. A similar problem expressed where n was to the power of 2, but that was meant amortized, so per vector pair, essentially. So now there is the other conjecture, which our conjecture is implied by that our conjecture, so we can reduce this OMV conjecture to our conjecture, which is also presented in the same paper, and is this the online matrix vector multiplication problem. And there the idea is that we have again an n by n Boolean matrix M, and we have these column vectors v1 to vn that arrive one after the other, and the goal is after seeing each vector vr, we want to output the multiplication of M with vr. Yeah, and this one here is actually also, the conjecture here is that there is no algorithm that solves it in subcubic time. Okay, so a lot of the proofs actually also in the original stock paper were done using the OUMV conjecture. They were conditional on that, but then later on, this one was also shown to be a valid one because it's actually also simpler. You don't have the pairs. For us, it's didactically, it's easier to actually work with the OUMV one. So what is the proof idea? Well, the proof idea is this. Assume there is an algorithm A that can maintain triangle detection query with amortized update time and this enumeration delay, okay, for some gamma. Now we want to design an algorithm B that uses the oracle A to solve OUMV in subcubic time, in N. And if we manage to do this, then we contradict the OUMV conjecture. Okay, so what is this algorithm B? First of all, we have to construct, given our OUMV instance, a database instance. So what do? Basically, we take the matrix M and we just simply store it in the relation S, right? So effectively, S at the indices I, J will just have the value which is given in the matrix M, so it will be 0 or 1. And in each round, okay, of the algorithm, we do this. We have relation R encoding the vector UR. Yeah. So again, we just store the vector in there. But because relation R was a binary relation, on the first column, we just put a constant A. So effectively, we make the query simpler, right? Instead of actually having the join also on the first column of R with the last column of T, there we put just a constant A, so it joins trivially. So we don't actually influence what happens on the other two columns on B and C. And similarly, in relation T, we encode the vector VR. So as I mentioned, on the second column of T, we just put A, the constant A, the same constant as here. And then it will be easy to see by the construction that essentially the result of multiplying these vectors and matrices is exactly QB. Yeah. And then we have to check whether QB is 1 using algorithm A. If we check that, it tells us essentially whether we'll basically solve our original problem on matrices. So let me show you an encoding for U, M, and V. Imagine that U is this one. I put it transposed. Yeah, I show it like a horizontal vector here, and it has only the second position, value 1. The rest is 0. Then the matrix has these ones, and the rest are 0. And the vector is this one here. Yeah, the vector V, which is now a column vector, right? So effectively, this index here 2 tells me I have to look at the second row, and this index 1 here tells me I have to look at the first column, right? And I find that indeed 1, 1, and 1, they make up a 1. Yeah. Now in databases, what happens is this. As I said, in relation R, I put A as the constant for the value of variable A, and then for B, I put the actual index for the 1 value. So we have just 1 value here, and the index is 2. And for that, I put the value of 1. For M, I just encode. Essentially, I just list all the coordinates of the values 1 in there, right? Like 2 and 1, 3 and 1, 1 and 2, 1 and 3, and 3 and 3. They are all here with value of 1. As you can see, I don't need to store actually the zeros, right? So this is a rather more compact encoding of the matrix, which is typically in databases. You don't put the values with a 0. Is what Val explained, that we don't need to store explicitly those that have an element of 0 in there. And for T, I do similarly. I have index 1 with the value 1, so it's 1 and A. So now if you do the join, what happens is that you have to take this 2, which is the row index. You look here whether you have the row index also 2, and then you look at the column index 1 and see whether you have it here. And it is the case, so then you multiply 1 and 1 and 1, and you get a 1. Yeah. So that's essentially the construction. So now let's actually look at the algorithm B, what it does. So first of all, I said that I have to take matrix M and populate the relation S. That takes at most n squared insertions. Then in each round, I have to delete all tuples in R and T to prepare it, or I could construct a new database with a new schema, let's say a relation R with index small r and T with index small r. So I do at most 2 n deletions. So these deletions do not really affect us in any way for the argument. And then we insert into R and T, which takes about 2 n insertions at most. Yeah, we just insert as I explained. Then we check whether QB is 1. So the holds if and only if our vector matrix vector multiplication is 1, and this means essentially, if I detail that there is an I and J such that I in UR is 1, that at position Mij is 1, and V at position J is 1. So then B constructs a database of this size, and the big N, the size of database, is O of n squared, small n squared. Yeah, good. So let's actually see the time analysis. So recall that A needs this amount of update time, where you see this, I replace the big N by n squared, yeah, and also I replace it here, the big N by n squared, yeah, for the delay. So how much to take here? Well, we have this amount of updates in worst case because we have this amount of entries in M, and for each of them it takes this update time. So that gives us something of this form, n to the power of 3 minus 2 gamma. Now let's see in each round what happens. We have 4 n updates because, in each of the 2 relations R and T, we delete first and then we insert. And for each of them, we have to do this update time. And this gives us something like O of n squared minus 2 gamma, where gamma is strictly positive, right? So this means this is subcubic, this is subquadratic. And then checking this, effectively means the answer time. We have to look at the delay. And the delay will be exactly this one here, because we have just a single value when we just want to access it. And that gives me also some quadratic time. So now this is for one round. If we actually take these two quantities and we multiply by n for all n rounds, we get something which is also subcubic here. So what is the effect? The effect is that the overall time will be something subcubic, which will contradict the OUMV conjecture. So this means that if we can solve our query faster than with the update time and the delay I mentioned before, this means that we can also solve the OUMV problem faster than it is conjecture. Good, so this is another tool we actually use, right, in IVM, which is very much largely borrowed from the algorithms community. Okay, so now the question is, can we close the complexity gap? I showed you some upper bounds, which are done using standard approaches, and I showed you a lower bound. Yes?
I just wanted to note that this reduction here is very similar to a reduction that occurs in Virginia in my paper from Fox 2010.
Yes.
In fact, we show with arbitrary polynomial time preprocessing, you still can't answer the query's subquadratic time.
So this is, yeah, this is excellent. So this is actually, for that I was mostly inspired by the Schweikart's paper from 2017 in PODS, but you know, I imagine there must be somewhere done before Borodin.
It's in our JACM paper.
Yes.
Okay. Not the entire thing you said. No.
Yes. But I'll reach out. I'll reach out to.
It's the similar stuff.
I want to say one more thing. When Nicole gave her talk about the equivalence of all pairs shortest paths to triangle, the same reduction works for the equivalence of Boolean matrix multiplication and regular triangle detection. And this OUMV problem is the dynamic version of triangle detection, whereas the OMV problem is the dynamic version of Boolean matrix multiplication. So you've essentially seen the equivalence of these two problems. You just have to make it dynamic.
Great, thank you so much for the extra clarification. So now let's see whether we can close the complexity gap. So we know we have this known upper bounds. Yeah, we have some known lower bounds now. Yeah, can we maintain the triangle count with sublinear update time is the question, and the answer is yes. We can maintain it with this amortized update time. And this would be worst case optimal. So let's see actually how we can achieve that. In fact, I will show you a very simple argument by which we can get this amortized update time for some parameter epsilon that can vary between 0 and 1, right? So, and then we get the space, which also can vary from linear to, in this case, to 1.5, yeah, to n to 1.5. And then we may have also some pre-processing time. That is, the time it takes initially to process. If we start with an empty database, of course, this will be a 0 pre-processing time. And the answer time remains O of 1 because this is a scalar query. But there are also other queries which are non-scalar, for which, of course, we also would like to understand the delay trade-off in here, which I will show you a bit later. So basically, the picture looks like this. So as we vary epsilon, we can actually get the space increasing and then decreasing, and the update time decreases and then increases. And then it reaches an optimality for epsilon is 0.5, for which amortized update time becomes essentially square root of n. Now, for the argument of this lecture, I will just use the simple, a rather simple approach, for which indeed the space can increase, but we have another, a slightly more involved argument that keeps the space linear, which then matches also what is actually known in the literature, that you don't need to increase the space to maintain this. So let's look inside. So there are several techniques we use in order to solve the problem like this. One is that we still need to compute delta queries the same way I showed you before. We still have to materialize views, like in the higher order IVM. But there is a new ingredient, which is basically adaptive processing based on data skew. Yeah. So we have to treat the heavy values different from light values in order to achieve that. So effectively, before you've seen this as there are specialized algorithms for the sparse domain and for the dense domain. Now we have to somehow put them under the same roof in a way. Yeah. So let's see how this proceeds. So we take relation R, right, out of the three relations, And we want to decompose it into two, into a light part and a heavy part. The light part should have essentially the values A that are paired with at most n2 epsilon values of B, right? And then we say that A is light. But in case we have an A prime whose number of B's is actually greater than n2 epsilon, then that would be considered heavy. Yeah? So we split the relation R like this into a light and a heavy part. And one interesting thing we can derive is that not only that, of course, A's, the light A's will appear in at most n2 epsilon tuples, but the fact that we can have at most n to 1 minus epsilon heavy guys. Because if each heavy guy has at least n to epsilon tuples, and there are n tuples overall, you cannot get more than n to 1 minus epsilon heavy guys. So these two upper bounds are actually important in our analysis of the algorithm afterwards. So likewise, we partition S and T, right? Partition on one of their variables. So we have then R partition on A, S partition on B, and T partition on C. Good. So now Q, our original query, will be the sum of all these queries, right? So we have the light part of R with the light part of S with the light part of T, sum up with all other combinations, the heavy with the light, and so on and so forth. So we have 2 times 2 times 2, 8 combinations. And then we'll have to look up and understand how they actually behave. So let's consider we have an update to R, and I put here a star to say that I don't care whether it's light or heavy, depending on alpha. I just I can look up and find out. Okay, let's say it is in the light part or is in the heavy part, and I will show you how basically each of these 4 cases can be considered under such an update, so that we can get the complexity I promised you from the very beginning. Now, what is crucial is that to evaluate these delta queries actually for each of these 4 cases, yeah, we have to use perhaps different strategies. We cannot use the very same strategy, the same, in database parlance, the same query plan, right? Because if we use the same query plan, then of course we would need to do the partitioning in the first place. Yeah? So we have to be sensitive to the heavy light partitioning. So these are the deltas now, right? We want to compute the delta of this first query that is light on B and light on C, and then we have this single tuple update, and where now in S and T we have we look at that part where the B value is beta, and here the A value is alpha, yeah, and so on and so forth for the others. And let's see, I think it is actually didactically interesting to see how this behaves. So if we look at the light part, yeah, so we are in this setting, right? We have alpha and beta, our tuple from delta R. And now we have in SL just this part, and in TL only this part. What happens is this, that we know B is actually light in S, right? So it can be paired with at most n to epsilon C values. Yeah. For T, we don't know much, because C is actually light, but we don't know for this A how many C's we may have. However, what we know is that we have to intersect this n to epsilon at most C values with some C values, and we can take the minimum of the 2 sets to give us the time to do the intersection. It is as if we iterate over the C's and then do lookups into this fragment to find out whether we have a matching pair. So the update time remains then n to epsilon, yeah, to intersect these lists, and that's it, right? So this is actually done. So that's already good, because if epsilon is actually below 1, then we have a sublinear update time. Now, if we look at the heavy case, right? So what means? It means that here the beta will be heavy, but this doesn't tell us much about how many C's. Well, it tells us that we have many C's, right? More than n to epsilon. But what happens here is that T being heavy on C tells us that we can have at most n to 1 minus epsilon C's, right? So this is the thing. So this is the constraint we use at the moment. So then the update time becomes O of n to 1 minus epsilon. Why? Because we have to intersect at most n to 1 minus epsilon C's with this C's in here. And we take the minimum of the 2. Good. So now let's look at the light and heavy combination. So we have light on beta. So the number of C's here is n to epsilon. And we also know that the number of C's here is actually upper bounded by n to 1 minus epsilon. So we know this, we know that. We take the minimum of the two. So we get this, right, in this particular case for the update. So, but there is an interesting case, which actually, can be set apart from the other three, namely that where we are heavy on S and light on T. Now, what does it mean? Well, 1 second. It means that basically we cannot really use, we know that beta is one of the heavy guys, right? So it exceeds n to epsilon. So we cannot use this as an upper bound. And here, we don't have anything on alpha to upper bound the number of C's we have. So we are a bit stuck at the moment, right? So what we could do at the moment is this. We can create a view, which materializes this joint of S and T. So we materialize, we project away C, and we keep this one. And once we have this view, of course, it's very easy to just do a lookup in the view, right, to check whether beta alpha are present here and then get their payloads. So the update time would be O of 1 in this case. But of course, what I did, I shifted the problem to the view in a way, right? So we could do that, and I will show you how we can do the views. But so far, what we got, this is the picture, right? So we have, in case of light and light, this is the update time. In case of heavy and heavy, this is the update time. Then for light and heavy, there are in fact two possibilities we can use. So we get this the minimum of the two. And then for the last one, we have O of 1. So overall, we get this update time, which is basically the maximum of this you see here. Yeah. Now let me go back to the view. So these are the auxiliary views we have to maintain. So we have to maintain for RNS in case this is heavy, this is light. Again, heavy, light, heavy, light. So this combination that actually created problem for us. So how can we do that? So imagine we have this view, and we want to have updates to S. Yeah. So we insert beta gamma into S. So then with gamma, we then do a lookup to find the A's. Now gamma being light in T gives us an upper bound on the number of A's paired with gamma. So that's actually good. It gives us essentially n to epsilon upper bound. Now, and that's the time for update to S. If we want to update T instead, with gamma and alpha, then in S, what we can see is that the number of B's here would be upper bounded by n to 1 minus epsilon because the B's are heavy. So again, we can maintain this view in a good time in n to 1 minus epsilon. And overall, the maintenance time for the views would be of this form, right? This is the maintenance complexity, and the space is given by this because we have to basically keep these views around. And these views cost us some extra space. Okay. So this is basically the maintenance strategy. Yes?
How do you know which case the input belongs to? Do you have to decide?
You can always look up and find out whether, for an alpha beta inserted in R, for instance, whether R belongs to the heavy guys or to the light guys. For instance, one possibility is that you just do a lookup in light R and then heavy R. Okay, so far it looks good. However, there is one particular caveat, namely that we depend so much on this light-heavy partitioning. So what happens if we start inserting a lot or deleting a lot, and our initial assumptions about heavy and light are not anymore correct, right? This is one thing. Another thing that may happen is that we start inserting so much or deleting so much that all our thresholds, which were based on some parameter n, size of the database at some time, becomes deprecated, right? We have to adjust for the new n, for the new size of the database. So this requires actually some rebalancing. So effectively, to do this, we have actually to account for some amortization, right? So we have to pay some price, accounting for the fact that every now and then these two situations may actually happen. So one situation is depicted here. We are in R light, A was light, but then we did so many insertions that suddenly A becomes heavy, right? So in that case, we'll have to transfer n to epsilon tuples from one part to the other part. right? So as soon as it gets, asymptotically over the threshold of an epsilon, we have to put it on the other side. And this time actually becomes the time of inserting all these n to epsilon tuples for that light value, previously light value, into the heavy part. So the time is max of epsilon to 1 minus epsilon to do one update. And then we have to do this n to epsilon times. Yeah. So the other one is when we change the heavy light threshold, so we change the size of the database. So the threshold was here, but now the threshold goes up. Yeah. And then whatever was considered heavy, for instance, now becomes light. Yeah. So in this case, what we have to do, we have to recompute partitions and views from scratch. And the time complexity will be this, right? Because this is basically the space we took. So all the views, all the tuples we have in there are proportional to this. Yeah. But what actually happens is that even though both forms of rebalancing require superlinear time, we don't have to do them eagerly after every update, right? So it is perfectly fine to wait for a number of updates, let's say, proportional to n to epsilon, before we actually do a minor rebalancing. And similarly, we can wait for something proportional to n, right, size of the database, number of updates, before we do a major rebalancing. So in a way, think of it as, you invest at the time you do an update, you invest extra tokens, right, for your insurance that, every now and then you may actually have to do this sort of major or minor rebalancing, right? But the number of tokens you have to invest with every update will remain constant. Good, so the overall amortized rebalancing time becomes this. Good. So there was actually follow-up work in TODS where we look at triangle queries with different free variables. So here I showed you only the case where we computed a scalar. But what happens if you want to output, for instance, the edges, right? Or, the triples that represent the triangles. And there we actually analyze various notions of optimality for these queries. There is actually from the algorithms community an extension of this algorithm to k-click counting and to a parallel batch dynamic triangle count algorithm based on our algorithm. And then in 2021, there was also by I think Yufei Tao, an extension to look at update time and approximation quality trade-offs for triangle counting, where basically they looked at the complexity of the triangle counting based on some notion, some property of the graph called arboricity. But open questions we have here would be this, yeah. We don't really understand much about the lower bounds in particular for general queries, functional aggregate queries. And I will come back to this in the second half of the lecture. And what we realize also is that the lower bounds give us, in worst case, a rather high, I would say, lower bound for single tuple updates, which makes actually batch updates at least asymptotically faster than doing single tuple updates. For instance, if you look at the queries, for those of you familiar with the Loomis-Whitney class of queries, where the triangle is just one of them, right? If you look at Loomis-Whitney 4, for instance, statically, you get a complexity of n to 4 over 3. But this lower bound is applicable there as well. So you can get a lower bound of, for a single tuple update of square root of n, so n to 1 over 2. But then if you then insert n tuples, you get the overall complexity of doing n inserts to the database n to 3 over 2, which is obviously higher than the n to 4 over 3, which is actually if you do it statically. So there are several issues related to this. Of course, one is to better understand this gap in complexity between doing single tuple updates and batch updates. This is one thing. Another thing is perhaps that the notion of this worst case analysis, for single tuple updates is not the right one. And perhaps, and especially in practice, we are actually most likely going for average complexity, right? So on average, it may be that, you get for the Loomis-Whitney I mentioned, a complexity of n to 1 over 3, which is less than what actually you see here. But the idea is that, some updates may cost more, some updates may cost less. But on average, they cost n to 1 over 3. Yeah. And there are actually some references I put here if you want the slides, so to follow up. And with this, I'm actually done for the first part of the lecture. And I take a question. Yes.
Thank you, Dan. Let's thank Dan. And yes, we have time for questions.
So there was one by Paris.
Yes, Paris.
So I was a bit confused about your last point because you talked about beyond worst case, but you're using an amortized notion, right? So you're already doing kind of an average case analysis of the update.
Well, I mean, it's a so the lower bound I showed you, right, is with a big O notation, right? That you cannot get of O of n to 1 over 2 minus gamma, right? So this means that you cannot get below that. But I can have, if I actually do a lot of inserts, let's say to the database, I may have some inserts that cost constant time.
Yes.
Right. But some of them may cost, I don't know, above n to 1 over 2.
Right.
Right. Okay. So that notion of complexity is different from the one you perhaps have in mind.
I see. So you want to average your amortized time somehow?
To amortize basically all the overall and to average over all the inserts. Right. So I get this sort of average complexity of it. So it's a bit the different notion. Yeah.
But do you really need to amortize? I mean, I'm thinking, as you were describing, so you're worried when n increases. But I could simply store the updates in a separate database, also of size up to n.
Yeah.
And answer query twice, once on the static database, once on this growing database. When that one reaches, well, I'm not sure. Maybe you update them on the side, maybe you do a little bit of work on a third database, and by the time you reach n, you have updated.
You're right that in practice I will never be as eager as I'm here in theory with the rebalancing, and in fact it hurts a lot. So we try to actually implement this to make it practical, and so far the jury's out. I mean, simply because if you do a simple delta is a very simple query, right? The logic is extremely simple. So even though for the heavy guys it may not do the best, amortize over all the light guys for which it does very fast, right? It will overall gain, much. It will be much faster than, let's say, every now and then checking the whether this is heavy, this is light. Even the simple if then else checking whether should I do it in the light case or should I do it in the heavy case is actually a problem, I would say, in practice. So I wouldn't do it, but it is true. You actually have you take a snapshot and you realize, okay, based on the snapshot I have here, these are light, these are heavy, I work with them. And very rarely you actually look at, whenever you don't have a huge workload, you actually try to rebalance. Yes. Yes.
So it's a related question. I mean, so you described the algorithm as so you gave an amortized bounds. Can't you actually do the rebuilding in the background?
Yes, definitely.
Worst case.
Yes.
Yeah,
So we have a sketch of that.
The same thing.
So we have a sketch of that. Basically, the amortizing the algorithm essentially. Yeah, and we can do this. Again, theoretically, yes, this is possible, and definitely we can do that. In practice, however, you don't want to spend that time, because you have to do extra work for the eventual situation that you might get there, to pay the price.
I should mention for people who don't know this, but unlike many theoreticians, Dan actually goes and implements this stuff, and he expects these algorithms to run better than state of the art, which is a completely different story. So, Val, you had a question.
No one. Okay. Yeah.
Yeah. So you are not using provenance at all. Provenance can be used for deletion tracking, right? You wouldn't gain anything if you were to do that. To just remember every tuple, how it was computed, and just.
Yeah. To be honest, we didn't really persuade. I mean, we looked into this actively. I can see perhaps some benefits. In some cases, you may do things faster. In particular, if you are not interested in, let's say, precise counts, you are interested only in the existence, right? I mean, the provenance can already tell you there is another derivation of that result, and then you can stop quickly, right? But we have to take into consideration the maintenance of the provenance itself, which actually costs time. So here, that was an issue we didn't. A reason why we didn't consider.
Yes, please.
So it seems that this is completely independent from the strategy for answering the initial query. So is that always the case? So,
The rebalancing.
Delta.
The rebalancing, you mean?
No, just because this is all to compute the delta Q, right? Like the delta to your query. So is this always independent from your initial query answering? So whatever strategy you might use to answer.
No, it depends. I mean, also for these delta queries, if I go to the question right, the question was, would the delta approach be independent of the queries? I mean, there is this meta idea that, you apply the delta and then you solve the query where one relation is replaced by a delta relation. So that is the same, right? It's a general concept. But of course, it depends how you actually execute the delta query on the actual query you have, right? And the sizes, the cardinalities, and other.
Right. I mean, rather than depending on the query itself, the strategy for computing the query, right? So we saw some of these strategies for computing queries on.
Yes, we do use that. So this query is such that you cannot really exploit too much structure. But for instance, if you have acyclic queries, alpha acyclic queries, then there, yes, you have a lot of structure that you can exploit in order to lower the complexity of doing the delta, right? And I will show you towards the end of the presentation, the second lecture, that basically you can get a notion of dynamic width, which depends on fractional hyperplane width, right? To basically express the complexity of doing the deltas. Yes.
So the strategy of splitting the relations into heavy and light components, how does that extend if you have multiple queries that you need to worry about? Say if R is used on two different queries, the triangle query and something else.
The answer is magic.
Yeah.
No, the answer is this. I mean, so far what we looked, we looked at the class of queries and we realized, by hand, which partitioning strategies would give us something. Because non-partitioning strategies can actually give you anything meaningful, right? Like improving the complexity. So that was actually pen and paper work. So there is no automatic approach. We can be right. For except that you do it for a couple of queries in a class, you realize that this might work, and then you try to prove that it works for all the queries in the class, and it lowers the complexity. I don't know if I answered the question.
Yeah, I'm just in general wondering if the subdivision into light and heavy should be adjusted based on like sort of a broader workload of queries.
This is what you mean.
Yeah.
Yes, it could be. We look here individually at each query, and we try to say something about the query. If you have several queries you want to evaluate together, then yes, that would be a multi-query optimization problem. And I think that, yes, it will make sense that, you go for a particular strategy which overall gives you best for the queries instead of giving you best individually for each query. Yes, you're right.
Okay, I propose we stop here, take a coffee break, and please feel free to talk to Dan during the break.